Okay, folks. Well, I hope you were able to figure out what to do with the video yesterday, and I hope that it looks like most of you were able to get the work done in the time that we had for that video. So I think 20 minutes is pretty good time. Hopefully, yesterday you were able to watch all the video. Didn't ask you to do too much work there, but as we go through the class and as we go through our online course here, there will be more work that you have to do, and so hopefully you're able to write down the answer that I asked you here, submit it on Classroom, and get that done. Okay, so I'll go ahead and take a look at that and check it off for you. Okay. Um, so hope if you have any questions, folks, please make sure you comment in Classroom or make sure you email me about any questions you may have about how we will be doing the class here with the discussion, with the lecture here. So make sure then, if you are concerned, make sure you come by this afternoon, 3:15 to 4:15, and get your questions answered. Okay. All right, so let's go ahead then and let's pick up where we left off with yesterday. Okay, so we are beginning our study of mechanics, and mechanics basically is the study of motion. In physics, that's the study of moving objects, and basically what we do in physics is we try to quantify all of the phenomena in the universe. So whatever we see, whatever we can observe in physics, what we try to do is we try to quantify that. We assign a number, which indicates the magnitude, and a unit to it, which indicates the particular physical phenomenon being observed. And so I think that's the hard part about physics for many people, is that they have a hard time understanding how we can take numbers and how we can take symbols and assign it to what we can observe in everyday life. And so the most common observation we can make in everyday life, for the most part, is just movement. And so mechanics is the study of movement in physics. And so with that said, then what we're going to do then is we are going to describe motion. We're going to describe motion using numbers and units. And so what we're going to do then is we're going to start out very simple. And we're going to start out by studying dynamics, which is basically the description of motion in a quantitative way, not just a qualitative way, but in a quantitative way as well. And specifically, we're going to focus on kinematics, which is the discussion and the description of motion in using without any reference to what causes that motion. Okay, so kinematics is what we're going to start out with in terms of our study of mechanics. I only will take you in this class as far as kinematics. For the rest of you, those of you who already taken it, mechanics is covered in physics. And for the rest of you, what you'll do then is, if you pursue your studies of physics, you'll get more of the mechanics at that point. Okay, so we need to understand kinematics here just on a very basic level. Okay. Engineering obviously is taking physics and making practical use of the physics. And so for those of you who are interested in getting into mechanical engineering or any type of engineering, engineering is the practical application of physics. And so I think for all of you folks who are thinking about getting into engineering, you will have to study physics eventually. So just keep that in mind. Okay. All right. So we started out then with this. We continued our discussion then of how we can indicate whether an object is moving or not. Okay, and so for us to do that, we have to agree upon certain things. How are we going to measure that motion? How are we going to measure then and agree then that the object has moved? And so we said then that we have to assign a scale. We have to assign a fairly arbitrary scale in order to determine then the object is in motion. And then we said then that the most basic way that we can describe that an object has moved is that it has changed its position. And so for us to determine whether an object has changed its position yet or not, we have to assign then a scale. We're going to go ahead and we're going to use two different coordinate axes. We're going to use the coordinate axis you see here. We have the X and Y axis. Okay, and then we're also going to use the plane polar coordinate axis, where we are going to use a coordinate and an angle. Okay, so this Cartesian graph here is what most of you are familiar with, in which you have an x-axis and a y-axis. The x-axis represents horizontal motion, and the y-axis for us is going to represent vertical motion. Because right now what we're going to do is we're going to focus on one-dimensional motion. So that means that we're only going to focus on an object moving on the horizontal, which is the x-axis, or the vertical, which is the y-axis. We'll talk about two-dimensional motion towards the end of this particular unit here, but for right now, we're going to focus on one-dimensional motion. And so we left off with this particular graph here. And so I told you then, we have three different frames here. We have the first frame, which shows then two objects that are at rest. We have the catcher here, who is in one position, and the truck here is in in a second position. This is going to be the first frame here is going to be the initial state. So if you can imagine then this being a movie. So the frame will move from 1, 2, and 3. So time will increase as we go from frame 1 to frame 2, frame 3. Okay, so that's why we have time increasing as we go down. This represents time initial. And so not only do we have to specify a specific coordinate axis, we have to also specify when we study moving objects, a time frame as well. Okay, and so the time frame here then, and again, this is all arbitrary. The time frame we're going to choose here then is at the initial position when both are when we are just starting to look at this phenomenon here, starting our observation. Well, we're going to say that time represents the initial time, which is going to be time 0. Okay, so make sure you keep that in mind. We always have to indicate a time frame as well as a physical frame, which we can analyze motion. Okay. All right, so the question and so we progressed through the second and third frame. Okay, so my question to you then yesterday is, how do we know then that this truck is moving? How do we know that the truck is moving? Well, first of all, the answer to this question is that time is increasing as we go from time equals 0. And I just arbitrarily pointed out then that 30 seconds later. Okay? So from 0 to 30 seconds, what do we see happening? We see the truck changing its position. Now, we said that along the x-axis here, we're going to arbitrarily call this point here, point 0, at 0 meters. Okay, so that's going to be 0 meters at this point. Wherever this truck is at, it is a certain distance away from 0 meters initially at time equals 0. Okay, then at time, and we'll say here at time, at the second time frame here, at the second frame time here would be 15 seconds later. Okay, so 15 seconds later, the truck then has moved towards you. It has changed its position from x initial here to x final here. Okay, so the change in position. So the change in position over a time interval is what allows us to describe then the motion of this object. So the truck then moves. Now, with that said, that if you take a look at the catcher, okay, the catcher doesn't move because from 0 to 15 to 30 seconds, the catcher here does not change his position. So let's say arbitrarily that he started out 20 meters away from the origin here. So he is 20 meters away from the origin. From 0 to 15 seconds, he stays at 20 meters. From 15 to 30 seconds, he stays at 20 meters. And so therefore, the catcher then has no displacement. He doesn't change his position because over time, he did not move. He did not leave this 20-meter mark. Okay, so with that said then, how do we recognize that there's motion? We recognize that there's motion when there is a change in position over a certain given time. Okay, all right, so that change in position, okay, let's go ahead and write this down. That change in position, we will indicate right now, since we're dealing with only horizontal motion, we're going to talk about then the change of position is the change in the x coordinate, the x position. Okay, and that change in delta here always represents a change. That change in can always be indicated by taking the final position and subtracting from it the initial position. Okay, and so that's how we know that an object has changed, has moved, that it has changed its position. Okay, now when we get to the discussion of vector quantities, we're going to see then that this change in position can also represent 0. How? If the object ends up where it started out at, then the overall change will be 0. But we'll get to that in just a moment. Okay? All right. So with that said, then let's go ahead and describe. Let's quickly go over this here. I think this is going to be review for many of you. If you don't remember this, make sure you come by and see me. Because motion, folks, is always directional. When an object moves, it moves in a certain direction. So we have to be able to describe the motion not only in terms of numerical, in terms of a quantitative measure, assign a number, assign a unit to it, but because motion is directional, all motion is directional. You're either moving to the left, you're moving to the right, you're moving up or you're moving down, and so forth. Because motion is directional, we also have to be able to indicate a direction to that particular, indicate direction to that description of motion. So if we're going to describe motion, to describe it completely, we have to also indicate the direction in which it moves. And so we have then, and we learned this already, a way that we can describe a particular physical quantity with a direction. So these are what are called vector quantities. Vector quantities then are just simply descriptions of nature that is directional. And so it has both magnitude and direction. And so we were able to indicate then there are different ways that we can indicate the vector quantity. But one of the simplest ways is by just simply using an arrow. Okay, another way that we can indicate a vector quantity is that typically you'll see this. You'll see the particular physical quantity and it will be in bold print. Okay, so scalar quantities will not have that. So for example here, a scalar quantity sets temperature. Temperature is not directional. So for example, 5 degrees Celsius. When we describe a temperature of 5 degrees Celsius, we're not saying then that temperature has any direction, so it doesn't. Mass also has no direction. It's just a quantity, and it has no direction to it. Same thing goes for work, which is heat, which is described then in terms of energy. And we'll hopefully if we get a chance this semester, we'll talk about that as well. But the scalar quantities on the right-hand side, what we see there is that those physical quantities, when we measure those quantities, there are no direction to it. However, if we take a look at the left-hand column, displacement, velocity, and acceleration, those all describe motion. We'll talk about those each in turn in this unit here, but because they all describe motion, those are all measured quantities. We can measure displacement, we can measure velocity, we can measure acceleration, because all those are measured quantities. We also, they all describe motion, we also have to include in our description then the direction in which each of these occur. Okay, so make sure you keep in mind then that vector quantities are all measured quantities. We can measure these in much the same way we can measure these, but the difference between vector quantities, these measured values here, and these measured values here, these have direction. And we have to indicate that direction when we write down the physical quantity. Okay? All right, but just like with scalar quantities, we can also add, subtract vector quantities, okay? And we learned that already. We learned that back in the first semester. And so make sure you keep that in mind. If we're going to use arrows to represent the vector quantities, use the tip to tail method. And we'll get a chance to review that a little bit in this unit as well. But make sure then that you remember that, okay? Okay. So with that said, then now we can describe a physical quantity known as displacement. Okay? Now, if you take a look at displacement, it looked a whole lot like how I described change in position, and it is, and it absolutely is, because displacement then is described then as the change in position with direction. We have to indicate the direction in which the object is changing its position. Okay? And so the calculation is exactly the same. How we calculate for the change in position, we take the final position and we subtract from that the initial position. However, the only difference now is we have to indicate a direction. Is the displacement to the left? Is it to the right? Is it up? Is it down? Is it north? Is it south? And so forth. So we have to make sure then with displacement then, which is a change in position, we also have to indicate the direction because displacement is a vector quantity. Now, understand this. Displacement and the total distance traveled are not the same thing. And make sure you understand why that is. The total distance traveled actually is a scalar quantity, whereas the displacement is a vector quantity. And so let's go ahead, and I want to give you an example here before we go on. Give you an example of displacement, and then we'll talk about the difference in between displacement and total distance traveled. Okay? All right, so let's go ahead and let's take a look at an example here. Okay, so we have a car. Okay, we have laid out the x-axis here. We've labeled and we've arbitrarily indicated that this position here is 0, where the speed limit sign is. That is what we call 0. Now, obviously, the car does not start on 0. If you take a look at this, the car does not start on 0, so therefore do not always assume that that an object starts from 0. So the initial position, x initial here, is going to be for the car at a distance that is 30 meters away from 0. So its initial position is 30 meters away from the point that we call 0. Okay? Then the car moves to this final position here, which is about 50 meters away from the 0 point. So the car here starts a distance 30 meters away from the from point 0, and it moves then to a distance, sorry about that, folks. Then it moves to a distance that is 30 meters, and then it moves to a distance then that is 50 meters away from 0. So both of these positions here, 30 meters here and 50 meters here, is relative to this 0 point right here. So this is where we call x is equal to 0 meters. That's an arbitrary position, okay? All right, so with that said then, the displacement, if we take a look at this, and let's go and take a look at it, okay? So we're gonna calculate the displacement from A to B. Okay, so x initial is going to be 30 meters, x final is going to be 52. Just a quick note on the symbols, the annotation here. I use x naught here, x naught meaning just initial starting position or starting, and in some textbooks you'll see this referred to as I as well. Okay, all right. So the displacement then is 22 meters. How did we get that? Well, let's go ahead and plug it in. Displacement then. And I'm going to write it with the bar on top since I can't make this into bold print. This indicates it's a vector quantity since we are dealing with displacement. It's going to be x final position minus x initial position, which is then going to be x final is 50 meters. Okay, and this should be 20. Sorry, that's a typo. 50 meters minus 30 meters here, which gives us a displacement of 20 meters. Okay, so 20 meters here. That's our net displacement. Understand this, we're not done with this yet. For this to be a vector quantity, we have to indicate direction. Now, the direction, and we'll talk about this in just a moment, is an arbitrary assignment as well. We indicate what direction is. However, there are conventions that we can use to help us help us from making simple mistakes. Okay? And that is, if we're dealing with an x-axis, okay, everything to the right of the x-axis is always indicated as positive. Everything to the left of the origin on an x-axis will always be negative. Okay? And we're going to stick with that because yes, even though direction is arbitrary, okay, you have whatever direction you choose to indicate the direction, whatever directions you choose to use, you have to be consistent with that direction, those directions throughout the problem. Because if you switch halfway through the problem, you're going to end up with the wrong answer. Okay, so make sure you keep that in mind. And so to avoid having those simple mistakes being done, we just stick with convention. Okay? So along the x-axis, everything to the right is going to be positive, everything to the left needs to be negative. And again, with the y-axis, if we had included in here, everything above the origin is going to be positive, everything below is going to be negative. So with that said, then the displacement of this car then is in the positive direction. So therefore, this is going to be a positive 20 meters. And what I would suggest you do initially then is just make sure you write these down in order to make sure then that you remember that it's 20. So this is the direction there in the positive direction. Okay, so the displacement here is going to be in the positive direction. Okay, so make sure you write that down. Okay, all right. What I'd like you to do then, real quick, on your paper, I want you to find the displacement represented in part 2 here. Okay, so find the displacement here, and I want you to find the displacement from point C to point F. So real quick, go ahead and do that. Okay, I'm going to pause here, and I want you to write this on your paper. Okay, and calculate for the displacement. Make sure you indicate direction as well for the car as it moves from point C to point F. Okay, go ahead and do that real quick. And we'll come back and then I'll work it out for you. Okay, hopefully you got that done. Okay, so let's go ahead and take a look at this here. So at point C here, now this is the initial position. Okay, this is initial position of point C, which is roughly about what, 40 meters to the right, 40 meters to the right. This time though, the object's gonna end up at point F here. At point F, which is x final then, it's at a position on the negative side of 0 here. So it ends up at a position that what's what, negative 50 meters. Okay. And so with that said, then let's go ahead and let's work this out. Okay. We have then the change in x, change in displacement, or change in x is going to be x final minus x initial. Okay. So therefore x final is negative 50 meters. So roughly about negative 50 meters minus, minus, write that in, minus a positive 40 meters, which gives us a displacement then of negative 90 meters. Okay, and if you notice there, the negative side is right there already. You'll notice that with a lot of these problems, if you do it correctly and you set it up correctly, the sign will be there. So what does this displacement tell us? It tells us then that the car then is moving in the negative direction, and it undergoes a displacement, a total displacement of 90 meters in the negative direction. Remember, vector quantities, when you have a negative sign, does not mean less than 0. You can't have a displacement that's less than 0. Understand what this answer means again. This answer means then that the cars undergo on a displacement of 90 meters from start to finish, but in the negative direction here. Okay, and so with that said then, roughly here, negative 91, the displacement is in the negative direction, so that's what we have right there, okay? All right, so with that said then, I'm running a little, I just ran out of time here, so what you'll post today then is this particular problem here that we just did. Just make sure you post that on Google Classroom, and then make sure you get that done. No extra problems for you to do today, okay? So make sure you keep it in mind. What we'll do is we'll continue to talk about displacement tomorrow. We'll talk about how we can physically represent, graphically represent this displacement, and then we'll continue on. We'll talk about this total distance travel and displacement, and hopefully we can get into the discussion of velocity tomorrow. Okay. All right, folks. So, like I said, make sure if you have any questions, comment. I'll be in front of my computer during our class time, so comment either in the classroom or email me. And then, like I said, if you have any questions that you want to ask me in person, or I'm sorry, live, join me at 3:15 to 4:15 after school today, and on Zoom, on our Zoom meeting, Zoom Meet page, and then I'll get your questions answered then. Okay. All right, folks. If I don't see you then, I will see you tomorrow.